Hey everyone, and welcome to section 8.2 about simplifying radical expressions. So we're going more in depth into looking at radical expressions. We're going to look at some stuff that's a little bit juicier than what we were looking at in the previous section. So let's get our bearings first. When we have a radical expression, it is said to be simplified if it doesn't have any factors of m raised to the n. So in other words, there are no nth powers left inside the radical to bring out. For example, if we look at 5, remember that when we are taking a square root, the index is really 2. So we want to see if we have any other factors of a number squared. We don't. Okay, so this guy would be simplified, but if we look at the square root of 12, 12 can be written as 3 times 4. And 3 times 4 can be rewritten as 3 times 2 squared. And that's the kind of thing we're talking about. So though square root of 12 is not simplified, we can use this property here to simplify it. The square root of 12 is equal to square root of 3 times 2 squared. But according to this property, we can write that as 2 separate radicals. And we know that the square root of 2 squared is just 2. So this is square root of 3 times 2. And it generally looks nicer if we have the non-radical number on the left side of the radical. So now we have 2 square root of 3, which is simplified because there are no other square factors inside the radical. You can do a similar kind of trick with division, which we'll talk about. Otherwise, we just got to crack into some practice. So we got some expressions here. These are just pretty harmless looking. Let's see, can I write 48 as a square times something? Well, I know I can write it as 16 times 3. And isn't 16 4 squared? So this simplifies to 4 square root of 3. Here we have the cube root of 729. Well, I don't know, but I do know that 729 is 9 times 81. And 81 is 9 squared. So actually, our answer is just going to be 9. How about that? How about that? For variables, it does work a little bit differently. Basically, if the power of the variable is larger than the index, then we use as many multiples of the index as we can without going over. So here 7 is bigger than 3. I could write x to the 7th as x cubed times x to the 1st. Each of these guys would be now in an individual radical. Of course, the cube root of x cubed is x, and again x. Then we have times the cube root of x. So we get x squared times the cube root of x. All right, next batch. Here we have p to the 9th. So how many times can we write p squared? P squared, p squared, p squared, times p squared, times p, each of those individual p squareds be the absolute value of p. So we get p to the fourth times the square root of p. So we get p to the fourth power times the square root of p as our final answer. Next up, we have y to the eighth. We can write that as y to the fifth times y cubed. So we're left with y times the fifth root of y cubed. And let's see, we have the square root of 72. 72 is not a perfect square. But 36 is. We can write this as 2 times 36 times n squared times n squared times n squared times n. So I get 6 absolute values of my n's, and I'm left with the square root of 2n. So 6 times the absolute value of n cubed times the square root of 2n. All right, we're warming up a little bit. Start to go a little bit faster. $180 is 36 times 5. Now what we could do is write out repeated multiplication of m squared, but we know that we have 9 total factors of m to work with, and we need 2 every time we want to use the square root, so to speak. So I could just kind of shorten it, say that I have m to the fourth squared times m. That gives me 9. And for n, I would have n to the fifth squared times n. So this is going to look like 6 times m to the fourth times, we need an absolute value around n to the fifth. It's an odd exponent. And we're left with 5mn in the radical. All right, what do we have here? We have square root of 80 x to the seventh y to the fourth. So this is 16 times 5. Another thing that we can do is we can just write the variable to a multiple of the index. Our index in this case is 2. So we want to write this guy as x to the sixth times x. That gives us x to the seventh. And y to the fourth, we can just leave as is. Of course, x to the sixth is really x to the third squared. Now what comes out of the radical? 16 x cubed squared and y to the fourth. Need absolute values around x to the third. It's an odd exponent. You know, when I take even roots of variables, I need absolute values. Get y squared, because y to the fourth is y squared times y squared, and inside I'm just left with 5x. All right, now let's look at some division. What we can do is rewrite to be square root of m to the sixth over square root of m to the fourth. And that's square root of m cubed squared over m squared squared. So this is m cubed over m squared. But I need an absolute value sign. I can write m cubed as m squared times m. M squared is always going to be positive, so that doesn't need an absolute value sign anymore, and I can divide out the m squareds. So I am left at the end of the day with absolute value of m. Of course, I could have also gone the root of applying our properties of exponents, I get the same thing. So it's up to you. All right, second example, I can, you know what, I'm going to apply the properties of exponents that we know and love so much. So we have x to the 13 minus 7. That's the cube root of x to the 6th, which is equal to the cube root of x squared cubed, or in other words, x squared. Now for this one, there's no reducing inside of the radical, so I really do have to resort to looking at separate radicals in the numerator and denominator. All right, now I know 108 is 27 times 4. And I know a to the 18th power. It's really a to the 6th power cubes. B to the 6th power is b squared cubes. The cube root of 27 is 3. 4 is not a perfect cube, so it's going to stay in there. I'm going to have a to the 6th. And then downstairs, I'm going to have b squared. How are we doing? We doing good? I'm doing good. Okay. Last set of examples for this section. Let's first do some simplifying. That's going to make our lives a whole lot easier. So I know I can reduce the fraction 18 over 32 to 9 over 16. And following rules of exponents, I'm going to be subtracting. So I would have p to the 5th minus 1. And q to the 7th minus 2. Okay. We can break this down even a little bit more. So I have square root of 9 over 16 times the square root of p squared squared, which would be p squared, times the square root of q squared squared, which is q squared, times the square root of q. Remember that quotient property of square roots means that I can take the square root of the top and bottom. So I'd have 3 over 4 times p squared times q squared times the square root of q. Similar kind of procedure for the next guy. And simplify my fraction to be 16 over 81. And I would have a to the 9 minus 3 times b to the 7 minus 3. All right. The fourth root of 16 is 2. And the fourth root of 81 is 3. So this would be 2 over 3 times the square root of a to the 4 would just be the absolute value of a, times the fourth root of b to the 4th, which would be the absolute value of b, times the fourth root of a squared. So this would be 2/3 the absolute value of ab times the fourth root of a squared. It's getting gross, folks. So that's about it. From here, we're going to look at using rational exponents. So we're going to turn exponents into fractions. I know that sounds terrible, but I feel like in some ways it makes our lives easier. So there's that to look forward to.